This type of chemistry can be used to do some really cool stuff as far as protecting groups. So you could use a alkyl chloroformine in order to protect an amine, and then you can actually get that amine back. So in this example up here, we're taking a primary amine, reacting it with benzyl chloroformate, and we ended up with a carbamate. Now we could also deprotect that amine, in other words, get the amine back through a couple different options. If you were to react this with hydrogen in the presence of palladium, you would end up getting the amine back. You would also get carbon dioxide from the decarboxylation of the carbonic acid that would be present, and you would also end up with toluene. So you can actually see here's your carbon dioxide, here's your toluene. Now, in the other conditions, hydrobromic acid and acetic acid, you're going to use a slightly different route here. You're going to end up with your amine, but it's going to be protonated, so you'll have an ammonium. You'll still get your carbon dioxide, just like you did before, but instead of ending up with toluene, you're going to end up adding a bromine onto it. So this would be benzyl bromide. Derivatives of carbonic acid tend to easily decarboxylate, which is the loss of one equivalent of carbon dioxide. So notice that in all of these molecules, you can actually see the carbon dioxide molecule within it, and then what's left over outside of that ends up being your leaving group. And all of these are driven forward by a couple different factors. One of the main ones in the case of these carbonic acid derivatives, these small molecules, the main driving force is that we are going from one molecule to two molecules. And that just makes entropy very, very happy. So we can also see decarboxylation of carboxylic acids, but it has to be a specific type. It has to be a beta keto acid. So a beta keto acid is a carboxylic acid that also has a carbonyl in the beta position. That could be a ketone or an aldehyde, or later we're going to see it could be a couple other carbonyl containing functional groups. Now, if you heat up a beta keto acid, you're going to end up losing an equivalent of carbon dioxide, which is decarboxylation. And you're also going to end up with a ketone or aldehyde or other carbonyl compound. Now, the number one mistake is that students end up losing the alpha carbons, so you want to make sure that you still end up with your alpha beta carbons. So the question is why? One of the big reasons is that a six-membered transition state is created if you were to rotate around the single bond between the alpha carbon and the carbonyl carbon of the carboxylic acid. You could end up creating a situation where through hydrogen bonding, you have a six-membered ring. And remember that six-membered rings are very stable, so they tend to be favorable. Now, when this is heated up and you lose your carbon dioxide, which you can see in the orange carbon and oxygen atoms, the electron movement that you're going to see is the oxygen grabbing the hydrogen. The electrons in the covalent bond between the oxygen and hydrogen will form a pi bond between the carboxylic acid carbonyl carbon and the oxygen. And then the covalent bond connecting the alpha carbon to the carboxylic acid is going to collapse as well to create a pi bond. And then that gives us our enol intermediate. Now, enols also will tautomerize very quickly to their keto form, and so we end up with a ketone as our product through tautomerization, which is something we are going to talk about a lot in chapter 18. Now, another thing that contributes to decarboxylation is that when you deprotonate the beta keto acid to have the carboxylate, and you go through the process of decarboxylation, the electrons on the oxygen are going to create a pi bond between the oxygen and the carbonyl carbon. These electrons are going to create a double bond between the two carbons and push the electrons up onto the oxygen for a loss of carbon dioxide, and you form an enolate. Now the enolate has a stabilizing resonance form where you can put the electrons onto the carbon. And that is going to stabilize that intermediate until it can pick up a proton to give you the keto form. And then, of course, the third reason is entropy. You start off with one molecule and you end up with two. Entropy loves that. So a special type of beta keto acid is a beta dicarboxylic acid. These are called malonic acids and malonic acid derivatives. So malonic acid is when you just have the dicarboxylic acid. And we'll see a lot of derivatives where R groups are added on to that central carbon, and that's what this example is using. So beta dicarboxylic acids, when they are heated up, are going to lose an equivalent of carbon dioxide, and you end up with a carboxylic acid that has the same R groups that we had before. And right now that doesn't seem like anything really interesting, but we're going to see in chapter 18 how this can actually be very useful. We can also experience decarboxylation through a carboxyl radical. So a carboxyl radical is going to be a carboxylic acid or carboxylate that has one extra electron. It's a radical. It's going to give us an alkyl radical and carbon dioxide in the products. So in order to do that, we're going to have homolysis of the bond there. One electron from the covalent bond is going to go in either direction upon heating. That's going to give us two carboxyl radicals. Notice we have a spare electron right here. And that's going to decarboxylate to give us carboxylic acid and an alkyl radical. So our last topic in chapter 17 are some pretty cool industrial synthetic uses of carboxylic acids and their derivatives. So in this case, we have a dicarboxylic acid, quite different from our malonic acid we saw a second ago though. This is called terephthalic acid. And then we're adding in a diol, in this case ethylene glycol, in the presence of acid and heat. Hopefully the alcohol, acid, and carboxylic acid in your head told you to go through esterification. And in this case, since we have a carboxylic acid on both sides of the molecule, and we have an alcohol on both sides of the alcohol molecule, we end up creating a repeating chain of esters. So we have our carboxylic acid containing molecule, we have our alcohol containing molecule. It's going to repeat n times and give us n equivalents of water. This is called a polyester, which is probably a familiar word. Another type of polymer that you can create through carboxylic acid derivative chemistry is to take a dicarboxylic acid and add in a diamine. This one is called 1,6-hexane diamine. And when it's reacted with a dicarboxylic acid, it gives us a polyamide. Polyamide is the organic chemistry word for nylon. Nylons are named by referencing the number of carbons that were in each piece of our starting materials. So we had 6 carbons in our dicarboxylic acid, 6 carbons in our diamine. So this is nylon 6,6.